Welcome to the deep dive. Today we're cutting through the complexity of a massive strategic meteorological assessment. It covers Europe, Western Russia, and the Caucasus for the end of November and early December 2025.
And you're looking at a 10-day period that is, well, it's far from a normal winter forecast.
Far from normal. How so?
The prognosis is for a severe two-phase hazard transition. What you need to know is that the intensity here is being dictated by these huge synchronized global forces. It's a real-time collision of climate volatility and, thermodynamic power.
Okay, so let's unpack this. We've got major weather coming, but what are these synchronized global triggers setting the whole thing off?
We see three main players. There's a persistent weak La Nina event. You've got these unusually warm sea surface temperatures, and then critically, a major disruption high up in the atmosphere.
A disruption?
We call it a sudden stratospheric warming, or SSW.
Wait, hold on, let's back up. What exactly is a sudden stratospheric warming, and why does something happening so high up affect our weather down here?
It's a really explosive, high-altitude temperature spike. It happens way, way above where our weather is. But crucially, it destabilizes the polar vortex.
The polar vortex, right. That's the ring of cold wind that usually keeps the chill bottled up over the Arctic.
Exactly. And this SSW event destabilizes it. It causes this lag effect that strongly favors a pattern we call the negative North Atlantic oscillation.
So this negative NAO, this giant pressure pattern, is essentially what opens the door to all the extreme cold.
Precisely. It enforces a north-south flow, what we call meridional flow. This pattern just slams the door shut on the mild maritime air that usually protects Europe, and instead, it forces frigid continental cold air deep into European Russia.
And that sets the stage for phase two.
That's right.
Okay, but before that deep freeze, phase I hits western and northwestern Europe from November 27th to the 30th. And this means intense wind and rain.
Correct. Phase I is dominated by a really active Atlantic storm track. It's bringing what some of the sources are calling bombastic cyclones.
Bombastic cyclones?
Yeah, rapidly intensifying storms. They're capable of winds up to 130 kilometers per hour. So you have to think about severe coastal flooding risks from high storm surges.
And here's where the climate signal becomes, well, unmissable. We see the influence of climate amplification just fueling these storms.
Absolutely. The warm sea surface temperatures across the Atlantic and Mediterranean are acting like a massive heat and moisture reservoir. They're just pumping energy into these systems.
And we can quantify that, can't we?
We can. Climate change has amplified the rainfall volume during these kinds of storms by about 15%, and it's increased the rainfall intensity by 20% compared to the pre-industrial climate. That extra moisture just makes these systems measurably worse.
Phase I sounds chaotic, but is it the main event? Where does the real danger shift next?
The main systemic threat that arrives in Phase 2, starting around December 1st, the high threat zone shifts eastward, concentrating from eastern Central Europe all the way across Western Russia.
And what's the biggest hazard there?
The single most consequential hazard is the extreme risk of widespread, debilitating freezing rain and glaze icing.
Now, that requires a very specific, a very delicate thermodynamic balance. How sure are we that those conditions will actually materialize?
We're extremely confident. The SSW-driven pattern, it basically guarantees a perfect thermodynamic trap. You get a razor-thin layer of air right at the surface at power line level that stays sub-freezing,
while warmer, wetter air moves in just above it.
Exactly. Moisture-laden maritime air slides right in overhead.
Yeah.
When that rain falls through the cold layer and hits the ground, it turns into pure glaze ice instantly.
That sounds catastrophic.
It is. That's where we're expecting systemic failure for infrastructure for transportation right across this collision zone.
And meanwhile, Russia's facing an unusually severe winter onset. We're talking temperatures below -20 Celsius.
It's a significant deviation for early December. And down in the Caucasus, the mountains amplify the hazard. They're facing extreme snow accumulations from the Black Sea, magnified by the geography. We could be talking up to 4 meters of snow in some valleys.
So the synthesis here is pretty clear. This 10-day period is a direct, real-time manifestation of large-scale climate variability. The SSW, La Nina, all supercharged by thermodynamic forcing from warm oceans.
That's the whole story. The measurable intensity across all these hazards, it just demands specialized preparation, especially for utilities against that crippling freezing rain potential.
You know, this raises a really interesting question for the future. As the planet warms, how does a threat like severe hail evolve?
It's fascinating because it becomes differentiated. High-resolution models suggest that hail frequency might actually decline in Central and Northern Europe by 2100.
It'll decline, so less hail.
The frequency, yes, because the freezing level is rising. However, in southern Europe and the Mediterranean, the storms that do form are projected to be significantly more destructive.
So the threat isn't disappearing, it's just shifting south and focusing its power where the ocean heat and moisture are strongest.
It creates a really complex challenge. What you need to consider moving forward is how our models track not just how often a storm occurs, but its destructive power, because that power is measurably increasing.